In this video, we're going to talk about designing a data lake. So a data lake provides a cost-effective platform for storing data for processing using business intelligence and analysis tools. The data lake acts as a single repository of data from multiple sources. The data should be stored in an immutable, raw state that it never has been deleted and never has been modified. So data coming into the lake can be structured, semi-structured, or unstructured. And because it will be coming from multiple sources, it can arrive in many formats. The format type is typically determined on several factors, but optimized format types like ORC and Parquet are preferred for their performance enhancements when data is being written to the data lake. Schema on read must be supported and implemented to build the schema as data is being read rather than as it is written. So data lakes are a versatile data store, providing supporting data services for many potential uses. Descriptive analysis refers to finding where problems occurred for the business based on data changes or anomalies. Diagnostic analysis helps to determine why problems happened by looking more deeply into the data and introducing external factors into the model to understand cause and effect. Predictive analysis is used by machine learning to predict outcomes, like component failure for anticipated lifespan based on wear analysis. Prescriptive analysis uses descriptive and predictive analysis to find the best course of action based on surrounding data. Self-driving cars and robots with intelligent decision-making are examples of AI uses of prescriptive analysis. Data mining is a broad discipline of data analytics that uses various models and methods to organize and find patterns, anomalies, and correlations in data. Typically, a data lake operates in a hub and spoke architecture. So a data lake must adhere to a standard set of determining characteristics. It must operate as a centralized data store for many remote systems, and data must be stored in a raw format through either streaming or batch writes. It must be capable of rapid ingestion, taking in large quantities of high-velocity data. Throughput and write speeds are critical to efficient data lake deployments. The lake must be capable of mapping data across sources, providing visibility to users through a secured entry point. A data catalog should accompany the data lake, detailing the data sets available and their characteristics. The data catalog should be updated automatically using metadata from the contents of the data lake. The data lake and related data manipulation, visualization, and analysis tools should be available as a self-service offering to users to provision their own compute and data storage. Now, creating an effective data lake is not a trivial task, and it comes with challenges that can easily cause it to become an uncoordinated mass of data that loses its value to the organization. So data governance must be put in place to ensure data is clean and relevant and can be reliably delivered to the users in a safe but user-friendly manner. A data swamp is a data lake that has run away, uncontrolled data structures, no clear lines of governance or delineations between data sources, and data that is not cleaned or classified effectively. Security must be assured on the contents of the data lake. This is usually enforced through access controls, and different zones should be included in your data architecture to move and manipulate data, providing access when they need it. Big data tools are still an emerging field, and that carries with the risk of being unable to find resources and skilled employees. There may be a considerable amount of experimentation and training involved with a data lake deployment. Now, data lakes are not a replacement for a data warehouse, and it should be clear what differentiates the two so they can be used effectively. So a data warehouse is a database optimized for relational data and contains only usable, cleansed, and formatted data that is presented directly from the warehouse to the consumer. Data lakes are different because they store multiple data types in multiple states. They are not limited to a relational data store on a single SQL platform. Now, data lake uses schema on read, whereas data warehouses create the schema on writing actions. Data warehouses are typically built and priced for rapid reads. A data lake is built for data throughput coming in and with high writing capacity. Data in a data warehouse is already cleansed, modeled, and validated. Data in the lake is raw and has not gone through any transformations or analysis. And data warehouses are typically targeted for business intelligence operations, whereas data lakes are used by data scientists, analysts, business intelligence, reporting, and visualization. The maturity of a data lake implementation can be measured by a series of well-defined steps. Initially, the lake will be capable of data ingestion and storage. Data will be written to and stored in a hierarchical namespace from various sources, and security structures are in place. Next comes sandboxing and experimentation by data scientists and analysts looking for the right models to create data sets that are usable by the business. The data lake becomes a complementary system to data warehouses within the organization. Data warehouses are used for targeting data, and data lake provides a repository for everything else. Finally, the data lake reaches full maturity when it becomes a central component within the organization's data architecture. Data operations default to the data lake, and the organization can retrieve any information about the business operations from it.
In this video, we're going to talk about big data file type planning. Now, data flowing into a data lake should be optimized for network throughput, write speed, and for parallelism for accelerating processing. The format of the data in the data lake is critical to achieving the goals, and there are a variety of file types available. An analysis of various factors can help to decide which one is suitable for applications. So formats will be either in a text file, a binary file, and these text files are human readable, compressible, and easier to use. However, they can be modified manually. Now, binary files require specific tools to create and consume them, but they provide higher performance for high velocity implementations through serialization. So there are two types of data. You have scalar and complex. Scalar data contains single values, whereas complex types contain multiple scalar types. Some formats do not allow the use of complex data types. So if your data is not a single value type, then these will be excluded from the option. A schema is not mandatory, but it can be kept with the data to validate the data set. The schema can be used by binary file types for encrypting the contents. Some file types do not allow for schema evolution, which is the ability to modify the schema definitions without affecting backwards compatibility of the schema with older data. Row-based formats provide support for OLTP situations, where maintaining high levels of data integrity when multiple users are accessing the environment is important. However, column-based OLAP or OLTP data deployments are more efficient for large data sets through avoiding excessive processing times and improved compression. Now, the way the data is transferred and written to storage will also affect file format decision-making process. So if the data lake is on a distributed file system like Hadoop HDFS, then parallelism can be introduced to provide faster data processing on binary files. If the system is able to read data at any point using splittable files, and if the files are not splittable, the entire file will need to be read, and partitioning will be the responsibility of the user. So reducing the size of the data being stored through compression can help reduce the read I/O and accelerate data delivery to the analysis engine. Column-based storage formats offer better compression than row-based formats, and text files are more compressible than binary. Some file formats are not suitable for streaming support and require batch transactional processing, so the specific use of the data must be analyzed to determine how it will be ingested. The surrounding organizational ecosystem may drive adoption of one format over another because of existing investments in tools that are optimized or otherwise unable to process certain formats. Now, there are important considerations for data collection when storing data in a data lake. So data encoding can have an impact on performance. The choice of JSON or XML, for example, can affect compression and processing speed. Batch sizes will affect both the data upload and access speeds. Performing large data refreshes can cause time-sensitive data to be outdated. Partitioning schema will also affect performance and can result in hotspots if not properly implemented. So it requires careful planning in advance of data writing. Now, a data catalog should be generated, and mechanisms should be implemented to automatically refresh and update it as new data gets added to the lake. The data catalog is used by data scientists and analysts to find data within the data lake. It contains metadata and is searchable, with descriptive information and the location of datasets relevant to the user. Users also use the catalog to find new data when it gets added to the lake. So the catalog should present new data sources in a way that highlights newly added sources. The catalog is built from the metadata attached to data as it is written. Processes for collecting metadata should be automated. The collected metadata is sorted, categorized, and assigned tags. Tags are automatically assigned to metadata entries according to their name. Machine learning engines can be adopted to perform this action. Now, building a data catalog is performed through a series of steps. So after the data has begun entering the data lake, you can begin the process of working with it to build the catalog. So the first step is extracting and collecting the metadata and placing it into the metadata store. Then the data must be sampled to get a clear view of the schema, database, and tables it is derived from. A naming convention should be applied to define the schema and utilize a common naming standard that can be communicated and understood by users referencing the catalog. A query log collects information about the datasets and provides additional information like data lineage and usability. So now that the technical aspect of the data catalog is prepared, it's time to optimize it through collaborative efforts with the users and data architect. The following are some best practices to follow when you are building a data catalog. The data set owner must be clearly defined, and the catalog itself should have contacts embedded, providing details for users to contact the owner if there is an issue or if they have questions about the data. Data catalog must have a robust search engine that enables datasets discovery for the consumers. Datasets must be verified before use to ensure they are usable. The data owner should prepare validation checks, and so should users, to ensure that there are no issues in the data refresh or transfer process. The catalog must be subject to data access security policies, ensuring unauthorized users do not have access to sensitive data through the catalog accidentally. In this video, we're going to talk about big data file formats. Now, selecting an appropriate file format for data residing in a data lake comes down to many factors, including the velocity, quantity, contents, and processing requirements of the data. So in this video, I'll review some of the most popular big data forms and their respective pros and cons for determining which is the most suitable for your environment. Now, comma-separated values are ambiguous, with most applications able to create or read them. They are provided in a human-readable text file with optional headers and new lines acting as record delimiters. So CSV is supported in both batch and streaming, but does not support schema evolution and does not adhere to a standard format, so may have processing issues in either occurrence. Now, files using CSV are compact and easily compressed with only a single write of the column headers. However, this limits it to flat data, requiring complex data structures to be processed separately. Due to the lack of specific character for splitting, only raw files can be split, provided they are uncompressed, or alternatively, they must use a splittable compression format that can be indexed like LZO. Null values and empty values are processed as the same within a CSV, creating concerns about data consistency. A JavaScript object notation, or JSON, is a text-based, partially structured key-value pair that is human-readable. JSON supports hierarchical structured data, storing relational data and complex relationships within single documents. JSON is used for transporting raw data between many web applications, so a variety of tools are available for validating the schema. While it is compressible, it is not as compact as binary file and repeats its column names, so uses basically more memory. It is suitable for both batch and streaming processes through excellent serialization libraries available for most languages. Metadata is stored with the data, and it supports schema evolution. Unfortunately, JSON files lack indexing abilities and suffer from an inability to be split, so parallel executions cannot be run. Now, Extensible Markup Language, or XML, was created for defining and coding syntax to standard documents that are both human and machine readable. XML supports batch and streaming and can be used to encapsulate and serialize data. Metadata is stored with the file, providing support for schema evolution. It is verbose, providing good compression ratios compared to other text-based formats. Now, because the syntax is redundant and XML files have open and close tags, they are not splittable and add high cost to storage, transport, and computational requirements. XML supports using namespaces for avoiding element naming conflicts, which can cause issues parsing. Now, Apache Hadoop is a framework for managing distributed processing and storage for big data initiatives using MapReduce. The Hadoop project, created with Avro file format, is an excellent choice. Avro is a row-based format used for serialization. It stores the data in a binary, but the schema in text. Avro is used for both writing persistent data and in wire format for data exchange between Hadoop nodes and clients passing data to Hadoop. And due to the format, it is compact and can handle large number of records. So the schema supports managing changing fields for adding and updating missing metadata, so it has strong evolution support and a low risk of backwards incompatibility problems. So when Avro is used for remote procedure calls, the client and server each possess a copy of other schema, which is passed over a handshake. So updates can be made retroactively and can be resolved by both sides without manual intervention. Apache Parquet is a file format designed in a joint effort between Cloudera and Twitter for use with Hadoop for efficient data analytics. Parquet files are binary and contain the metadata within the file, stored at the end and written once. Parquet files are column-based and support high levels of compression with formats like Snappy. However, this does result in no support for data modification. Online analytical processing applications are well suited to using Parquet files due to its columnar format and wide table support. Schema evolution is supported to an extent. Additional columns can be added to the schema, and the data source can merge schemas across files to add columns, but modifications to the existing column can cause compatibility problems with older data so it has to be looked at carefully. Parquet files are supported only for batch operations. Because Parquet is very well suited to aggregation over a particular column within the dataset and is optimized for read processes, it is the preferred format for business intelligence operations. Parquet supports prediction pushdown, which is a highly compressible and is in a binary format. All these factors combine to make extremely efficient and fast processing support for big data operations that encompass very large data sets. Optimized Row Columnar Format, ORC, was designed specifically for Apache Hive, a database warehousing solution for distributing data querying. ORC files contain groups of rows called stripes and a file footer containing data types, like the number of rows in the stripe and the number of columns as well as their data type are all available. Data in ORC is column-based, so it is best used for OLAP applications. However, this also means it is more compressible than any other format. But it also means it is limited to batch operations only, and the ORC blocks are presented in a non-modifiable blob without any append capabilities, so data must be recreated if modifications are made. The schema can be modified forwards and backwards by adding or removing columns, but does not contain the rich schema evolution capabilities of similar formats like Avro. And stripes are typically up to 250 megabytes in size, enabling efficient reading when used in Hadoop ecosystem. Protocol buffers is a file format from Google that was open sourced in 2008. It supports carrying communication across networks and data storage similar to JSON or XML. Protocol buffers is a language and platform neutral, making it highly portable. Typical uses for protocol buffers are in serializing data for transport between applications, and it supports validation within the code used to exchange messages. Protocol buffers requires a reference file with the schema because it does not carry with it the data, but it has strong support for schema evolution. And because the whole file must be processed on read, protocol buffer does not fit large file sizes well, so it should be limited to small serial data chunks and perform very well for stream processing, but not batch. In this video, we're going to talk about designing table storage for querying. Now, Azure Table Storage is a service built on the Azure Storage Platform for data storage for scalable apps that use JSON to serialize data. Now, table storage is used for large, flexible, non-relational data sets that can be semi-structured or structured. So table storage is a NoSQL service that can be accessed within your cloud subscription or exposed to accept calls over the internet, and it can support an unlimited number of entries up to a maximum of the storage account's capacity. Now, because rows can all be unique, the application can be flexible in their data access without requiring a schema to reference, meaning the table schema can evolve on the fly. Now, the Azure storage libraries can be used to perform advanced operations against table storage and are available for multiple programming languages, including C++, .NET Framework, Java, Android, Node.js, Ruby, Python, and PHP. Alternatively, the storage can be accessed through an expressed REST API and over HTTP and HTTPS. Designing non-relational table stores are different from a traditional relational database, so best practices have been developed to ensure efficient reads and writes. So consider the queries that will run against the storage. Choosing the correct partition key and row key can have significant effects on the latency of the queries. Table storage is cheap, but access costs may result in unanticipated expense. Denormalizing data will reduce access costs at the expense of storage. but this should still result in a cost reduction and improved performance. Hot partitions will reduce the query speed and increase latency of operations. Partitions should be spread out evenly, so requests are dispersed across multiple partitions. Now, storing duplicate copies of data can enable more efficient querying using different partition keys. So choosing the right partition key and row key is critical to the performance of queries run against table storage, and understanding the different file types and queries that will help you to determine the most appropriate keys, as well as formulate queries for effective data manipulation. Now, point queries specify both the partition and row key values to locate individual entities. And by specifying both, they are the most efficient and have the least latency. A query range uses a range of row key values, but only one partition key to return a series of results. The row key is a filter to return subsets of entities within the partition defined using the partition key. So a partition key scan type of query uses a partition key to specify the partition, but uses another non-key property for the filter. Table scan searches all partitions within the table for any matches to the row key. This is the least efficient query type and will slow down as the table grows. So querying and modifying values in the table are two distinct operations, and often optimizing one comes at the cost of decreasing performance of the other. So the system and its use should be evaluated and designed for optimal performance of read or write depending on its use, or a balance of both scenarios that will excel at neither. So there are two design patterns that can help design an application for optimal writing or modifying data in a table. So the compound key pattern uses the row key values in point queries to perform lookups. Using multiple row keys means the query can reduce or remove heavy join operations that otherwise affect performance. Results can be parsed by implementing separator character. Entity group transactions are a form of atomic transaction where the entire operation succeeds or the entire operation fails, ensuring consistency in operations and avoiding partial data changes. Now, an alternative method is to use the log tail pattern. The log tail pattern uses row key values to retrieve the most recently added entries, making it at a high performance option for recent data, but slower for older data. So if you choose to adopt this method, the data should be stored using the row key in reverse date order. The reverse tick value should be padded up front with leading zeros for sorting order enforcement. Now, because it uses the most recently written values, the log tail pattern can cause hotspots in the storage, potentially impacting query performance. Indexing in table storage happens automatically, using the row key and partition key values in a single index. Following standard design patterns can help you optimize query performance by working with the table, even though it does not have secondary indexes. The intra-partition secondary index stores multiple copies of entities within the same partition, but using different values for the row key. It uses more storage space, but provides a fast lookup and multiple sort order possibilities. The inter-partition secondary index uses different partitions or even independent tables to store multiple copies of the same data using different row keys, breaking up the data for retrieval to accelerate queries. Index entities are used for efficiently returning lists of entities by using an index entity. Relational databases usually will use data normalization to minimize redundancy and implement declarative querying across the models that define entities and their relationship. However, no SQL uses different mapping mechanisms, so requires an alternate approach to domain models. So a one-to-one relationship in a table must also include a link between the two entities that have a relationship for when they are situations when both must be retrieved, for example. Typically, for a one-to-many relationship, the common property would be an entity, and entities that leverage it would be linked using implicit relationships using the partition key. However, in table storage, these can be denormalized, and the entities would contain all relevant information at the cost of additional storage consumed and the inability to perform entity group transactions. Now, joins can be offloaded onto the client rather than performing them within the table. The entities can be kept independent and passed off to the client for processing. The table service supports storing heterogeneous entities, so classes used in an inheritance relationship can be persisted to other entities within the table by defining the entity class as it relates to the parent entity. In this video, we're going to talk about dynamic data pruning. Data stored in a data lake does not have indexes, so partitioning is a key factor in ensuring performance when Databricks executes a query. Partition pruning is a performance optimization to reduce how much Databricks reads when executing a query. Now, when a singles file is stored on a data storage service like Azure Blob Storage, it is written as several extents. A query cannot execute against the extents, so they cannot be used for partitioning, and pruning cannot ignore them and query only the relevant parts. However, they still affect parallelism, so it should be considered when queries are executing against files that they are executing against many components that look like a single file. File-level partitioning splits the data sets into relevant groupings of files and then defines the data frame across those groups. Files can be selectively ignored to improve performance by reducing the processing requirements. Folder partitions allow data to be organized into a folder structure with parent and subfolders that follow the Hive syntax in the attribute equals value format. So Databricks will automatically follow those structures for partitioning and selecting ignoring data. For example, if folders were named corresponding to the year of the data collected, a query could be formulated to request only data from the current year, which Databricks will use as an index to only retrieve information from the appropriately named folder, ignoring the other years. Nested data structures can improve the performance of Databricks, querying through predicate and projection pushdown filtering. Predicate pushdown filters out data before the query executes by pushing the query down through the nested data structure to only the relevant data folders and its contents using where and filter clauses. This affects the number of rows returned. So, predicate pushdowns can be very attractive to use for in-memory operations, as those where clauses can remain in memory as it reduces and works through the data set. Now, projection pushdown affects the columns returned by specifying only which columns are selected using the select clause. So care should be taken to avoid having many small files or too many oversized files when using pushdown to avoid inefficient parallelism. Static partition pruning selects the partition during compiling, ignoring the specified partitions, whereas dynamic partition pruning occurs during parsing. All right, so when a query is executed against a data set, the engine scans all available data within the source. Then the records that were indicated acts as a filter, and the system filtered out all non-relevant data, returning only the data not filtered out. Partition filters can be implemented, but this requires an in-depth knowledge of the data structures and the partitions containing the data. A partition filter removes all partitions not specifically queried against, drastically reducing the amount of data scanned and processed. So static data pruning carries many challenges because it's rare for simple queries to exist against flat data. Dimensional tables and complex queries and joins are common in the real world. When dimensional tables are implemented, the filter will only apply to one side of a join operation when the fact and dimension tables are joined for a query. An intermediate table can be created by first joining the fact and dimension tables external to the join for a single source of truth that can be queried directly to include all relevant data. This would result in significant data duplication and be inefficient to manage. Dynamic partition pruning attempts to solve the issues with static partition pruning. Data frames and data sets are submitted to the Spark engine, which translates them into its logical query plan. Spark then applies rule-based transformations to optimize the logical plan. It finds the dimensional filter and propagates it across the join, applying it to all relevant tables. Physical level optimization executes the computation across the cluster to perform the query and filter the results, reusing them in table scans to accelerate future queries. Dynamic file pruning is another optimization available in Databricks. It also optimizes query speeds by skipping data, though in this case it's at the file level rather than partitions. It is enabled by default in the Databricks runtime, but requires the data storage to be running data lake or delta lake. The join must be of the types inner or left semi only. It must be using the broadcast hash join strategy. And the files in the inner table must be of greater quantity than the value specified in the spark.databricks.optimizer.delta table files threshold parameter, which is defaulted at 1000. In this video, we're going to talk about designing a folder structure. Now, because a data lake is used to hold many types of data from multiple sources, the structure of the data as it is ingested is critical to ensuring its performance and usability. A data lake without clear structure is referred to as a data swamp and can quickly turn into a burden instead of a benefit. A well-structured data lake aids in enforcing security controls and auditing. A data swamp could expose data to the wrong users or result in a security breach. Having documented standards and conventions will offer a clean, efficient, reusable model for future data sources being added to the data lake without disrupting existing processing. Users can navigate the structure to obtain what they require, and the data catalog should evolve with the metadata changes without requiring significant management overhead. Governance practices for metadata management, information lifecycle management, and quality controls should be enforceable to all contents of the data lake. Now, when data lake is being deployed, there are various best practices to help with achieving the goals previously mentioned. Partitioning data lake by date is common practice, but can often lead to questioning where the date should be in the folder name. So keeping it at the front can help speed up pruning activities to reduce the amount of data processed, but putting it at the end of the folder name helps with security controls. Now, security is rarely set up by date, but it is frequently set up by subject area or source. So having data with the source name first and the year later can help with ensuring security is going to be effective, as well as users aiding them to identify their required sources quickly. Data zones can be created to separate data transformations. Zones are logical divisions of data in various states.
used to record the results of data manipulation to prepare it for the next step. While they are not a physical divide, other than in the folder structure, they can help with ensuring source data is kept immutable. Cleansed data has irrelevant entries removed, and the presentation data is correct and curated for the users analyzing it. Nested elements should be avoided. Security is difficult to enforce and will require more management, and query performance can be affected because it is required to process all elements. So storing big data coming from multiple sources comes with various challenges, not just from the storage perspective, but also from a usability and planning perspective. It is difficult to make changes once data is committed, so strategic planning can save a lot of headaches later. The volume of data can become unmanageable. Too many sources introduced before their data is well cataloged and governed can create a data swamp very quickly. So, keeping structured, semi-structured, and unstructured data in check, all within the same data lake, can be very time-consuming and complex. Data velocity is a measure of both how quickly it enters the data lake, as well as the time taken to transform and cleanse in advance of the consumers gaining access to it. So this can cause bottlenecks in other systems or put unnecessary strain on certain components within the system that could result in failure. The accuracy of the data may be skewed by other metrics becoming unbalanced. If data is outdated because of the queuing due to high velocity, then it could produce unreliable results during analysis. So the organization of the data lake can be influenced by many factors, and understanding them and their effects can help to mitigate issues that may come up if they are not factored in. So partitioning strategies can be affected by the data source and its capabilities. Partitioning by time is frequently used strategy. However, it can cause hotspots in storage if your queries access data by date. The data loading from various sources can affect performance of the storage. Streaming and batch loads can occur simultaneously, but timing multiple batch loads at the same time or with an overlap could cause drastic performance problems. So the source applications can influence data source, data storage, and ingestion. Internet of Things or IoT sensors will have and behave differently to more traditional applications that copy data on a schedule. Security boundaries and delineations between users and groups, captured data and data transformation activities can influence folder structures, the data catalog, and presentation zones within the data lake. Downstream activities and uses of the data will also influence folder structure. Users performing BI tasks will require different data sets to users performing predictive analytics. The data owner may have and define a different structure from a folder perspective than the data lake architect. Organizations with multiple departments residing within the data lake may have different owners with different requirements and methods for managing their data. So this is an example of a folder structure for a data lake, but organizational circumstances may vary, so it should be used as a suggestion or template only. The parent folder is where raw data lands when it is written to the data lake. Then, source folders are categorized by the source type. Within the source folders, there would be a substructure of source systems. And these source systems would be a complete comprehensive list of everything that could enter the data lake. Then, within the source system folders, there are new folder structures for each entity, partitioned out even more by folders defining the year, the month, and the day for data pruning to be accurate to within a day. In this video, we're going to talk about data lake zones. Now, the governance and access controls over data should be applicable based on its usage and consumer requirements, not as a universal decision made over all data as a single entity. Data zones within a data lake can act as separators of the data for different consumers, exercising different governance controls over each zone. So data zones are not a physical barrier, but a logical one, with different folder structures and different data sets derived from the zone before them. So each zone will be accessed by a different consumer. So this layout enhances governance principles and provides clear delineation of lifecycle management, providing self-service capabilities and data transformation and management tasks. Service level agreements can be drawn across different zones to ensure data is relevant and available to consumers when they need it the most. Security and access controls can be implemented at each zone to keep the zones relevant and the data within protected from unauthorized access, whether it is deliberate or not. Now, the raw zone is the landing area for data from within the governance. Because data is still in its raw format, generally it is not ready for consumption. Usually this means data will come at high velocity. So the primary requirements for the raw zone are large amounts of storage throughput and high write speed availability. So all data sources should be captured, so this zone will generally be the largest consumer of space and have a lot of unusable or unused data. Now, due to the raw nature of the data, it will consist of all attributes and columns from all sources, so we'll need transformation efforts applied to remove unused information. And data in the raw zone should be immutable. It cannot be deleted or modified because it is source. It can be copied and transformed for the following zones. Now, the structured zone is the next step in the zoning process. So let's get into it. This is where data that has undergone the first stage of transformation is copied to. These transformations might be to remove unused fields or clean up system data that is not relevant. And this zone provides a basic structure to the data that provides some value over the contents of the raw zone. Data in the structured zone should be contained within a typed tables, bringing unstructured data from the raw zone into a structured or semi-structured state. Now, automation should be employed to copy data into the structured zone. This zone is where most data scientists will start their analysis, so it should be kept up to date and not require heavy manual manipulation to keep populated. Now, data in the curated zone is a setup further than the structured zone for data transformations and cleansing. Data in the curated zone implements a canonical data model to combine and consolidate data from multiple sources. Data warehouses may extract data from the curated zone, or the zone can act as a data warehouse itself. Integrity checks for referential integrity and missing data are run at this zone to ensure data consistency and reliability. Because data has already been accessed for quality, data in this zone is consumer ready. Data in the curated zone is subject to being combined from multiple sources, so the data catalog must be updated to reflect the sources and the net effect of the combination data for consumers to fully understand the implications. Now, the serving zone is where data is moved to a fully ingestible state. So it acts as a data access point for consumers, providing a public portal that consumers can access. This is where data restrictions and access policies are enforced, limiting the data sets published to the consumer. The portal acts as a data mart, publishing the data sets. It provides endpoint capabilities for the consumer to connect to. The data catalog publishes its details in an easily browsable interface, along with references and related data, like the contact details for the data owner. The exploratory zone is used for data scientists to explore the data in various states and from multiple sources. So this zone acts as a testing area for trying out new models and analysis tools or methods without affecting production data or being constrained to data sets that have already undergone transformations that may remove relevant data. The exploratory zone should also allow the data scientists to add their own data for combinations and modeling for further analysis. The core purpose of the exploratory zone is for experimentation, so automated data refreshes and loose access controls should be promoted. But sensitive data should be removed from it as it enters this zone. In this video, we're going to discuss storage archiving tiers. Now, Azure Blob Storage is a service on the Microsoft Cloud Platform for hosting any kind of data. So Blob Storage is optimized for any form of data and is best used for unstructured data types. The Blob Storage service can serve files to a browser over HTTP or HTTPS, so it can be used for file transfers or for hosting static websites. It can also be used for streaming video and audio files through front-end players or as a source for content delivery networks. Any form of the file can be stored in the Blob service without any constraints for file size or file type. And the files can be presented to and used by many other Azure services for application purposes or analysis. So the Blob Storage service supports 3 forms of blobs that each fill a different need. The blob type is specified when it is created, but it cannot be changed later. So, block blobs are made up of multiple blocks to a maximum of 50,000, each of which has a unique identity. Blocks can be modified and referenced by their block ID. Now, append blobs support appending data to the blob. When the blob is modified, the new blocks are added to the end, making them ideal for operations like writing logs. Blocks cannot be modified once they are written. Page blobs are fixed-size blobs optimized for random access. Pages are 512 bytes, and writes can overwrite a single page or multiple pages. So blob storage supports 3 access tiers for the most cost-efficient storage and archiving features for data that is infrequently or never accessed. So starting off, the hot tier is the standard tier for data that is accessed frequently or needs to be readily available. It comes with the highest storage cost, but the lowest access cost. The cool tier is for data infrequently accessed or accessed only once per 30-day cycle. Storage costs are lower, but accessing data in this will incur higher billing than the hot tier. The archive tier is cold storage for data that is rarely or never accessed. Data is not immediately available and will require rehydrating to access it. The storage costs are the lowest, but if data is retrieved within 180 days of it entering the archive tier, it will incur relatively significant costs for access. The Blob Lifecycle Management feature can be used to provide management services to data stored in the Blob storage service. So, Blob Lifecycle Management is a set of rules-based policies that are applied to the storage account and can be scoped into specific blob types. It provides functions like moving data between tiers automatically. As data becomes inactive, or if it ages out, it can be moved from hot to cold tier to save on storage costs, or from cool to hot. Lifecycle management policies can also automatically achieve or archive data as it reaches thresholds of days since the last modification. This can only be applied to block blobs. Finally, as files exceed their usefulness, the policies can automatically delete blobs based on their age or based on tags. So the archive tier stores data offline for low-cost, long-term retention. Data in the archive tier cannot be read or modified, but the metadata will persist, so data about the blob can be retrieved. Data that has been archived can be retrieved in one of 2 ways. You can rehydrate the blob, which moves it out of storage into either a cool or hot tier in the same storage account by invoking the set blob tier operation. So effectively, it will no longer be in the archive. The other option is to copy the blob out into a cool or hot tier using the copy blob operation and specifying a new name for the new file when it has been written. So both operations will incur additional read and data retrieval fees, and priority can be assigned to accelerate delivery at additional cost. Additionally, copying the blob will incur rote operation charges, but it does eliminate the early deletion fee that rehydrating can bring if the blob has been archived for less than 180 days. Immutable blobs are an option for storing data in a way that protects it from the modification or deletion. It is used to provide a write once, read many, or worm storage operation where the data may be read repeatedly, but is never written to or otherwise modified. So this can be used for many scenarios like compliance for healthcare and financial institutions where they are required to retain data for many years. Immutable blobs can help with many other situations that require retention, with controls that can set retention policies that administrators cannot override. Legal holds involving litigation or for company policy can be put on files within Azure storage. The storage will prevent any modifications or deletions and log any access attempts. A legal hold must have an alphanumeric tag associated with it that will be used as the identifier string. Now, retention can be time-based, so when the blob is set to an immutable state, a time policy can be configured. When the time retention policy period expires, the blob can be deleted, or the policy can be extended. Logging will be retained for the lifetime of the immutable blob policy and contains the ID of who tried to access it, the command they ran, timestamps, and the legal hold tag if applicable. In this demo, we're going to take a look at archiving, rehydrating, and automating lifecycle management of data in Azure Blob Storage. So Azure Blob Storage offers the ability to move data between tiers for cost-effective data management. Archiving data is performed by simply moving data into the archive tier, and then if it is needed again, moving it back to an online tier. So Blob Storage is available within a storage account. So I'm logged into portal.azure.com, and my first step is to do that account lookup. So I have one that already exists. I'm just going to type into the search resources text box, SSDP. I'll bring this storage account up so we can take a quick peek at its characteristics. I can see that this is a standard hot access tier, locally redundant storage, LRS, and it's a storage v2 general purpose type. Okay, I'm going to scroll down here and I'm going to look for containers. So I find containers here. I'm going to go ahead and click on that. And I can see a single entry. So I will click on my entry that I've created. So inside the blob storage container, I have two files here. I have a 7zip.exe, which is in the hot access tier. Notice that it says it's inferred. All right, so in the access tier column, hot inferred. Now this is because when I was deploying this storage account, I was able to select whether the default access tier would be hot or cool. And I selected hot. So when the blob was updated or uploaded, it landed it in the hot tier by default. Now, I'm going to put this 7-zip file into the archive by changing its tier type. All right, so for that, I'm going to go ahead and click on the actual file name itself, and I'll get a new panel that's going to pop up. In the navigation menu that controls the functions for this file, there is a button called Change Tier. I'm going to go ahead and click on that. Now, from the drop-down list, I can expand the selection and see all the options. We have hot, inferred, cool, and archive. So you're going to notice that when archive tier is selected, I'm going to go ahead and do that, you're going to get a notification below the dropdown. The blob will be unavailable until it is rehydrated back to the hot or cool tier, and that this may take some time. I understand that. I'm going to go ahead and click on Save. Now, this time I will rehydrate a blob from archive. I will close this 7zip.exe panel by clicking the X button, and that will take me back to the contents of the container. I'm going to click on the other file that I had here, hwmonitor.exe. Now the process to rehydrate is the same as archiving. You move the blob into the relevant tier, except it is not an instant process. So I'm going to go ahead and click on the Change Tier button link again here, and Access Tier in the drop-down. It's currently selected as Archive. I will now change this to Hot. Now I can set a priority for the rehydrate process. Standard and High. Selecting High priority will retrieve the file faster, but it will incur additional cost. It should be reserved for emergency restores only. I will leave this as Standard and click the Save button. When the rehydrate process has been completed, the file will be fully accessible and will show as being in the Hot tier again. Now I'll demonstrate the Lifecycle Management utility available to blob storage. Using my breadcrumb, I am now going to go back a little bit into SSDP, which is that top-level storage account showing my available containers. In the storage account options, I'm going to scroll down, and it's under the blob service section. It's called Lifecycle Management. I'm going to go ahead and click that link to bring this up. Lifecycle Management is a rule-based policy for managing data within the storage account by automating movement between tiers, archiving, and deletion based on age or tags. This is all rule-driven. I will click the button link, Add a Rule. Now, rules are comprised of rules and actions and can have filters applied to narrow their scope to applying to only specific blobs in the storage account. I'll deploy a policy to automatically archive files after 30 days of inactivity. I'll give this a name, which is mandatory. I'll call it Auto Archive. All right. Now, the rule scope allows you to select blobs based on naming conventions or by tags associated to them. Or you can leave it open to apply to all blobs in the storage account. So I'll go ahead and leave that open. Just apply rule to all blobs in the storage account. Let me just scroll down a little bit here. Now, the block type. So the block type also acts as a filter. I need to select only block or append blocks, or selecting both. You can also further narrow it by selecting if the rules should apply only to those base blobs, snapshots of the blobs, and versions if your storage account has versioning enabled. Okay, we're going to now go ahead and click on Next here. And here are the rules that can be applied. By default, last modified rule is already put in place. I'm going to archive any blob that has not been modified in 30 days. So I'm going to enter my value into the field provided in the If section. So I'm just going to click on that If, and then more than days ago, I'm just going to place on 30 here. And then I'm going to click on the Add. See that rule here. So it just popped out, so I can see the name, Auto Archive. Come back in here, and I can see, when I click on Next again, base blobs haven't been modified in 30 days. So I can see that rule. And I can also edit it very quickly again here if I change my mind. Now, there's an additional setting. Before I clicked on Save on that last one, there is a Then clause. And by default is delete the blob. Let me go ahead and select that because we have some additional options that are here. Instead of deleting the blob, what I really want to do is move to the archive storage. So first we have move to cool storage. So this is for infrequently accessed data that you want to keep on cool storage for at least 30 days. And then we have move to the archive storage, used if you don't need online access and want to keep the object for 180 days or longer. So to properly complete this task, this is the one I need. I'll go ahead and select on that and then press the update. And this is why I wanted to show you this, because you can save, but you can go back in and update at any time. So the rule has been created and will apply to the storage account. Rules can be enabled and disabled. Or if you prefer to create the JSON that the rule will follow, you can enter it directly into the code view. So in this course, we've examined how to plan a data structure for efficient storage and transactions. We did this by exploring data lake design, big data file type planning, and file formats. How to design table storage for querying, dynamic data pruning in Databricks, efficient folder structure design, and data lake zones. Then we looked at storage archiving tier, data archiving, rehydrating, and lifecycle management. In our next course, we'll move on to examine data partitioning strategies and how to design for performance.